So in this video, we're going to be talking about VSEPR theory. And we're going to cover just the 5 basic shapes today. So our goals are going to be to define and introduce VSEPR. We're going to be defining steric number, coordination number, and bond angle, even though steric number will be the main goal for discussing in this video. And then we're going to define electron and molecular geometries. We'll identify the electron geometries based on the steric number in this lecture, and then next time work on doing more of the molecular geometries and the coordination numbers. So first off, what is VSEPR? It stands for valence shell electron pair repulsion. This explains the shape of molecules by stating that our negatively charged electrons, or in other words, all of our electrons, are going to repel each other, and they want to be as far away as possible. So the basic principle is anytime that you have an electron group, whether that be a group of bonds or an electron pair, they're going to repel each other and stay far away from each other. This won't come into play too much in this lecture, but it's important to note, and we'll talk about it more in the next, that electron pairs are going to show more repulsion than bond groups. Now notice I keep saying bond groups rather than just saying bonds. That's because single bonds, double bonds, and triple bonds are all going to be treated the same way. So let's start with some definitions. First off, steric number. These are your bonded atoms plus your lone pairs. Notice I say bonded atoms, or we could say bond groups, not just bonds. That's because your single, double, and triple bonds are all going to count as the same. Now, coordination number. This is your number of bonded atoms. Again, not number of bonds. Your single, double, and triple bonds are all going to count the same. So let's take a few examples. First off, NH3. We can count the number of bonded atoms, which is 3. We can count the number of lone pairs, which is 1. Remember, the lone pair counts as 1, not 2. It's a pair, not 2 electrons. So our steric number is 4, and our coordination number is 3. Next one. We have bromine with 5 fluorines. So we have 5 bonded atoms, we have 1 lone pair, which leaves us with a steric number of 6, or a coordination number of 5. Now lastly, I have one that has a double bond in there, just to kind of reiterate that double bonds are treated the same as single bonds. So here we have 4 bonded atoms. Even though we have 5 bonds, we just have 4 bonded atoms and no lone pairs. And so that gives us a steric number of 4 with a coordination number of 4 as well. Now a few more definitions. Today we're going to focus on when our electron and our molecular geometries are the same, and then in the next lecture we'll talk about when they're different. So don't let the fact that they happen to all be the same today be confusing. These are actually very different topics. The electron geometry is where I say quote unquote if you can see the electron pairs. Now with the molecular geometry, the electron pairs still affect the geometry. It still changes the way that the bonds are rearranged. However, we're not seeing the lone pairs when we're actually figuring out the geometries. So it affects the geometry, but it doesn't factor into, I guess, how we name it. Bond angle is relatively self-explanatory. It's the angle between the bonds. So we'll look at a couple of examples here. I don't want you to get tied up in the names quite yet because we haven't actually introduced them. We're going to do that over the course of the next 2 lectures, but just to kind of show you what I'm talking about. So here we're going to go back to phosphorus pentafluoride. This has no lone pairs, and whenever you don't have any lone pairs, your electron and molecular geometries are going to be the same. It's what we're focusing on in today's lecture. So this is going to be called a trigonal bipyramidal geometry. We'll talk about why later, and that's the same for both the electron and the molecular geometry. Notice whenever I say that we're saying that there's no lone pairs, I'm always going to be talking about the central element. Now this changes a little bit if you have lone pairs. So now let's look at the BRF5. For BRF5, you have a lone pair on the central bromine, and so our electron and molecular geometries aren't the same. We'll talk about all these names in a minute, but our electron geometry is octahedral for this, whereas for our molecular geometry, we have a square planar. And I purposely drew it in sort of the geometry that it looks like so that you can see it a little bit even if we don't actually know the names yet. So make sure before going on in this video, you've downloaded the worksheet and you have it sitting in front of you and you're filling it out with me. We're just going to focus on the first column today, And then in the next lecture, we'll be focusing on the rest, because this sets us up to do just the 5 basic shapes without any electron pairs to worry about. And you really want to have this down before moving on. So this is today's focus. Make sure you get this off the website. For each of the steric numbers, we're going to walk through and find the associated shape. You need to make sure that you know the names of these, as well as knowing what they look like. You might say, well, I don't care what they look like. You can't test me on that. But if you don't know this, it's going to cause you problems later on. You're not going to know how to do polarities. You're not going to be able to tell various other things later on. And so I don't care whether you know the names and then use the shapes and then think about the names to figure out the shapes, or whether you know the shapes and use that to help you with the names, but make sure you know both. And then in future videos, we're going to do the rest of these and deal with the lone pairs. So let's start out by walking through each steric number. Remember, our goal here is to separate everything as far as possible. So for steric number 2, we have 2 groups of things. 2 things that we need to space out as far apart as possible. So think about what this would look like. If you're not a particularly visual person, this is a good time to pull out toothpicks or ink pens or markers or something that you can kind of move around and play with. For 2, it's pretty straightforward though. You're going to want it in a straight line. Now, we try in chemistry to have things make as much sense as possible. So if you were going to name this, I think a good name for it would be linear. And thankfully, so did the people who decided to actually name this and got a say in it. Our bond angles for most of these, you don't have to memorize. You shouldn't sit down with this table and just walk through and memorize it. You should think about it. You know what a straight line looks like. You know that that's everything as far apart as possible. So you know that that has to be a 180-degree angle because they're directly across from each other. The same thing is going to be true of steric number 3. So we're going to go ahead and do this one on the same slide. If you think about 3 things that you want to space out as far apart as possible, and again, maybe playing with your toothpicks or ink pens or whatever you have handy if need be, these are all going to be directly in a triangle. So here we have a little animation that shows you what it looks like so that you can see it from all the angles. Now it's 3 points. We know that that shape is a triangle, and it's all on one plane. It's not in a pyramid shape or anything like that, so it's called trigonal planar. The bond angles for this one too, you don't need to worry about memorizing because we know that all the way around in a circle is 360 degrees. And if you divide 360 by 3, you get 120. So no need to memorize that one either, just think about what it looks like. Now let's do steric number 4. This one's a little bit more complicated. The most common thing when I ask people to go ahead and try to figure out the shape here is to try to put it all on one plane like we did for trigonal planar. For trigonal planar, that really is as far apart as everything as you can get, but that's not going to be true for steric number 4. So this is a really common answer and it's wrong. This is not what steric number 4 looks like. It needs to all be in 3 dimensions to get everything as far apart as possible. And so we have this. Kind of take a second and just look at the shape, see what it's doing. And you can see that this is using all 3 dimensions. It's not all on one plane anymore. Now, if you think about what would happen if you sort of put a cloth over all of that and you got a 3-dimensional shape, that would have 4 faces. So it's a tetrahedron. And so we call it tetrahedral. This one you're probably going to have to memorize the bond angle for. If you're really good at deriving geometrical things, you can think about this as the corners of a cube. Probably you're just going to memorize this as 109.5 and be all set. So it makes a tetrahedron, 4 corners, it's 109.5. Now steric number 5. This one's even a little bit more complicated than the last ones. For this one, we're even going to actually have 2 different types of atoms that we'll have to talk about. So I think the easiest way to picture this one, I'm just going to show it to you first, is to picture it as sort of a linear molecule combined with a trigonal planar. And if you could picture that, you'll see that you have a trigonal planar geometry and that you have 2 of them stacked on top of each other, or trigonal bipyramidal. Now, with this, the bond angles are going to be different. And I showed you this, I kind of spoilers with this one, because it's a little bit harder to see than some of the other ones. And so that you can see that there's a 90-degree bond angle and a 120-degree bond angle. This is as far apart as you can get all of the bonds. And so it's got to be in this geometry. But when we start talking about, especially next lecture, when we have to put on lone pairs, we have to have a way of describing this. I can't just, if I'm talking to somebody else, say, oh, this one or that one. They're not going to know what I'm talking about unless I have a model in front of me. So let's superimpose a globe on this for a minute, because it's the easiest way to remember it. Now, the one running straight up and down the globe, we have axes running up and down the globes, those are called axial. The ones going around, or in the trigonal planar type shape, are called equatorial. And so that gives us a way of talking about these different atoms. So we have two different bond angles for this one. We have the ones that are around the triangle in the center, which are equatorial. Those are 90-degree, or excuse me, those are 120-degree bond angles. And then we have our axial running down the middle, which is 180 all the way around, split in two, is 90. So this one might take a little bit more time to kind of think about. I would suggest building a model of it, even if you just take a gummy bear or something and stab it with some toothpicks so that you can see what's going on. It's a little bit easier in actual physical space as opposed to animations. Now our last one. Thankfully, this one goes back to being a little bit more simple. We kind of peaked out on difficulty with Steric number 5. So for this one, we still want to separate everything as far apart as possible, but since we have 6, it's just going to be, if you think about an XYZ coordinate system, it's going to be like that. It's just one on each coordinate system. All of the axes are the same because they're all going to be 90 degrees. Now, this one's called octahedral, and that's a little bit confusing at first because you're saying this is Steric number 6 and yet we're calling it octahedral. Doesn't octa mean 8? It does, but you need to think about the three-dimensional shape if you put this over top of the entire atom. And so that's why I have the little octahedron drawn off to the side. The octahedron actually has 6 points, but 8 faces. And so it's describing the three-dimensional shape rather than the hexa that you would think, because it's not talking about the 6 corners, it's talking about the 8 faces. So make sure you know that. Make sure you know that that's why it's octahedral, even though it's Steric number 6. Because we're on basically an XYZ coordinate system, our bond angles are 90 degrees. And that's another one of those, you probably don't have to memorize it, you can just kind of see it. So in quick summary of everything, we went through and we talked about the 5 basic shapes. So our 5 basic shapes, we didn't talk about anything with electron pairs on our central atom. We're going to do that next time. But make sure you have this down first because everything else is going to build off these 5 shapes. So we use our lone pairs and our bonded atoms to figure out these 5 basic shapes. Those are our electron geometries. Now, everything we talked about today also had just the bonded atoms, no lone pairs. And so our electron and molecular geometries were the same. This isn't going to happen in the next video where we add in lone pairs too. So be sure you know all of these by both picture and name. So you should be able to, even if you can't draw, you should be able to picture it. We generally won't make you draw things, but you'll need to know the pictures in order to answer certain questions.